All right, so we'll go ahead and get started. Welcome everyone here in the room and those of you who are online to the last LEAP lecture in high data science of the semester. My name is Galen McKinley. I'm the Deputy Director of the LEAP Center. And it's my great pleasure to introduce Jakob Runge, Professor Dr. Jakob Runge, for his lecture. He is the head of the Causal Inference group at the German Aerospace Center Institute of Data Science in Jena, and also chair of quantum informatics at TU Berlin since 2021. He studied physics at Humboldt University of Berlin and got his PhD at Potsdam Institute for Climate Impact Research. He has won several prestigious awards, including a fellowship award for complex systems from the James S. McDowell Foundation in 2014, and also an ERC starting grant in 2020. And we're very excited to have you here today to talk about causal inference and causal discovery. After the lecture, we'll take questions, and then I hope people can stay around for the LEAP holiday party that will begin soon after. So take it away.
Yeah, thanks a lot. Thanks for the introduction. It's great to be back in New York. I think I was in December 2019, just before the pandemic. But I was here also visiting Columbia, but not this nice new innovation hub. So that's a very nice environment to do science. Yeah, so my intention is to give a broad overview over causal inference and causal discovery with some perspective on machine learning and some more applications in earth sciences, more from an illustrative point of view to kind of walk you through how such a causal analysis can go and what to be aware of. Yeah, so that's a big, small picture of my group. We, as was introduced, work on causal discovery, causal inference, and collaborate a lot with climate scientists. So we are getting our inspiration for our methods and new developments from applied sciences, from climate science, and that is our mission. And with that, I start with a slight step back to reflect on machine learning in science and engineering, which is a topic that has been quite gaining attraction in the past decade. Not least since people like Emil Kuhn, Geoffrey Hinton, and Joshua Bengio, and of course, standing representatively for many others, have done really nice new methods and work that are enabling us today to do machine learning tasks such as object classification and localization. So topics like that have not been feasible a few decades ago are now in reach that you could come with say are through or going towards artificial intelligence. And while this is a real-life data where we see this being applied a lot, these methods are also gaining traction in earth sciences a lot. There's an explosion of works on using these methods in problems such as pattern classification, as shown here in a nice review article from Markus Reichstein. And from a static task set to more dynamic task set, as you might be finding more useful for the dynamical system Earth. We have here the analogy of video prediction and tasks like short-term forecasting. But the point I want to make here is rather that these methods really show their capabilities and their power in learning from very, very complex data sets, nonlinear relations from nonlinear data. And on the other hand, it's still all based on statistical associations. So we learn how things relate to each other. And that's why you find in the literature then often like avoiding causal terminology, like something causes another thing, that you would rather say that leads or lags, or you find descriptions like we find a relationship, association. And with all this, the mantra in mind that correlation is not causation. But on the other hand, while you are kind of restricting yourself in the language and the kind of conclusions you are willing to draw from such analysis, the problems we have across the earth sciences, for example, are all kind of causal questions. We don't want to know what is associated with extremes. We want to know what causes extremes. We want to understand, it's shown here, the causal mechanisms of like aerosol cloud interactions to be able to better represent these, for example, in climate models and improve the uncertainties of global projections, or on a more local scale, ecosystem respiration, understanding the causal drivings and quantifying these factors in such systems. And another topic is teleconnection networks. Atmospheric teleconnections has been a topic I've worked more on in the past. So these are our causal questions. And how do we get at this? Will be the big topic of my talk. But before, I want to give you a little bit of an intuition where applying machine learning just a little bit blindly to data can go wrong. And I do that with this toy model, which is really, really simple underlying. It is here illustrated in a causal graph where y is just a function of all the variables that have an arrow towards y, like here x6 and x1. And then x1 causes x3, x2 causes x1, x5 is just completely independent, and y causes x4 here. So that's my setup to illustrate kind of all the different ways how variables can relate to. And with that toy model, it's a linear system underlying. I generate data, and I will generate then the training distribution as one realization of these variables, and then I generate a test distribution, and many of these in the end, in order to then assess how well we can predict. And the target variable will always be y here. And now I will iterate through different choices of these axes, different feature choices. So when we do now linear regression here, and we choose as inputs x1 and x6 as causes, it's kind of my baseline now. We get a prediction here, the ground truth on the x-axis, and y hat is the prediction with this model. Of course, there's never a perfect prediction. And here I constructed this to have a root mean squared error of 1. And now what if we use not just x1 and x6, the ones that have actually an arrow towards y, the causal parents, as we call these, but we use all variables except for x4. Maybe because we know that, well, x4 really cannot be a cause of y. It is in this case actually caused by y. So we might choose just these. What we get is another prediction with a slightly higher prediction error. Maybe you could phrase this as, well, we are overfitting, we put in too many variables, there's too much complexity in the model, we should prune it or something. That's all points in this direction. And finally, I will include the variable x4 here in the model, essentially all variables then. And now a little interactive, I ask you, what do you think is the root mean squared error going to be? Is it going to be higher or lower or the same? Any intuition? So I'm using a linear regression model of y on all of these variables where the data was generated with this underlying causal relations. And I'm predicting testing my prediction on another realization. Goes down. Some consensus here. Okay, that's right. The error actually goes down. And the reason is to be discussed in the next slides when I show you how this can go wrong. But before, I will show kind of the same results, not with linear regression, but the same inputs, but with a neural net as a prediction model. And here, because the underlying ground truth is linear, the linear regression is kind of the best model, not the least misspecified model. And the neural net is doing a quite well job. And we have the same qualitative behavior. Root mean square error goes up for this one, and it goes down for this one when you use all data. And now with neural nets, you always have this interpretation problem, but there are ways to do so, such as with Shapley values. I think many of you are familiar. I'm not going to explain this much. I've seen them in some of the discussion we talked about these. So Shapley values, they measure the average marginal contribution, as I say here, of each of these inputs across all combinations of choosing them. And this is just to show that, all right, x1 and x6 are quite relevant here with that this is red and this is blue, meaning just there's a positive contribution here. But we also measure a contribution of x3. So I'm actually assessing this neural net here with these input features, and x2, and also a little bit x5, even though you might argue that this is kind of whatever is the noise that is coming from a finite sample. But still, there's certainly a significant influence contribution by x3 here, even though x3 is not really directly causing y, but is just caused by x1, which also causes y. So there's a correlation between x3 and y that is being picked up by the neural net here for some reason. And if I, on the other hand, go to this neural net here, where all variables are included, then we get this strong contribution from x4 here, is expected. Now, we step back and change the setup, where we now are not predicting in the same distribution. By the way, I mean, sometimes people say out of sample. So there's a difference between in the same distribution, but out of sample. So that's just from the same distribution, another sample. And that's what I do here. Of course, you should always predict out of sample. But here the setup was in the same distribution. And now we look for a prediction in a change distribution, where what I change here is, if you look closely at the data, I just add some factor, some constant mean change to the variable x4 here. So I just switch it up. And if you look closely, what then happens to all the models that use x4 as a prediction is that they get biased, right? They have this strong offset here. And the neural net pretty high, and also the linear regression pretty high. So that is basically the mistake you make when you use predictors that are not causal predictors, and they are not robust under changes in distributions, especially if a change happens in that variable, of course. Another thing is, what if I change x3 here? As you remember, here the neural net was picking up a lot of this, and therefore you get a stronger also decline in prediction performance with this model. And similarly, if you have a intervention or a change of distribution in this variable x5 here, this will also mess with all those models that use x5, even though it is actually not needed from a causal perspective in this prediction setup. So that's an illustration really of what can go wrong if we just do not think about causality in picking input features for our neural nets. So causal inference is trying to avoid that, or can be combined with machine learning to avoid such behavior. And if I had to put it in one sentence, then I would maybe say that causal inference is a framework to answer causal questions from observational and or experimental data. And giving credit to the people who have developed this over the past decades, Judah Pearl and Spiritus Gleamer Shines, the Pittsburgh group, and even a Nobel Prize was given last year to the economists, of course. No Nobel Prize exists for computer science, and that is quite, a nice award for this field. So I'm picking up here this table from Pearl's book, the Book of Y on the right-hand side, which is a popular science book, a nice bad night read that gives you a lot of kind of anecdotal stories about causal inference and gives you a good intuition of this topic. And in this book, Pearl frames causal inference on different hierarchies that are pertaining to causal questions you have. And on the lowest rung ladder of causation, we have association, and then he frames this kind of vividly as the activity of seeing. We just observe the system and may ask questions as what is, how are variables related, and that is where all of machine learning, basically most of machine learning that is not in the upper layers here, works, pattern recognition, correlation network, maybe purely statistical weather forecast. And then the other questions that I posed a little bit, where the questions we have in the sciences often are about causal relations. So they might be phrased as intervening, like the thought of experiment of what if I actually not just observe what variable X does and then look at variable Y, but what happens if I would be able to intervene in variable X and see how that changes the distribution of Y. So there's a change in notation and a mathematical formalization of this that I will show in the next slides. So this is kind of the question, what if I do? What causes what in the data? And then on even another level, a more difficult level even of reasoning is that of counterfactuals, which has another type of notation. And that activity here is about retrospection. So the question is not what if I do or what causes what, but the question is what if I had done, given that I have done something previously, different previously. So what was it aspirin that stopped my headache, for example? So the information that enters here is also the information of the current system, given maybe under another intervention. And you want to know that what should I have done in order to have a different outcome, for example. So the most basic question here, why? Did climate change cause this extreme event? So what climate change, what climate science often does is exactly answering counterfactuals using climate models. So a few slides on the basic underlying framework of causal inference. And there's two frameworks. There's the potential outcome framework, which is prominent in the social sciences and is not really using causal graphs so much. They frame their assumptions more in algebraic assumptions. So I'm tending more towards this framework. I think it's more intuitive, and they are theoretically actually equivalent. So that's why not go for this? And in this framework, you assume an underlying structural causal model, an SCM, with an associated graph. So for example, here in this aerosol cloud environmental factor toy example, we would, when we draw such a graph, at the same time assume that there's some equation, some more precisely assignment function for each of the three variables. XA is assigned the value f, like a function of its parents, which is here xe, and some eta a, which is a noise term, which stands for unresolved processes that are, however, assumed to be independent. So eta a, eta c, and eta e here are assumed independent, and they are maybe in the if these are climate variables, then this eta might be some local weather factors that only contribute to aerosols, but not to clouds directly, not directly. And we have an equation for each of the three nodes, where we have any functional relationship of the variable on its parents in the graph. So whenever you have an edge here coming from one node, then that means that the function here depends on this node in a non-trivial way. All right, so for this causal framework here to work, you don't see any time index here, and that's why it's in principle not using time per se. It doesn't kind of need it. Of course, you might then have the underlying assumption that first there's a cause and then there's an effect. And in this framework, also these graphs are in principle assumed to be acyclic. You can also work with cyclic models to some extent. It's just more challenging. But I will make the point later that if you resolve these systems in time, if you unfold the graphs in time, then often you all talk about feedbacks all the time, but a feedback might well be resolved as acyclic in a time-resolved manner. I will show that later. But now it's just important to understand that drawing these graphs implies you assume an underlying SCM, and there's a distribution on these noises. And now this important notion of P of Y do X, like this, what is called really the causal, the interventional distribution on which you base causal effects, is now defined by an operation on these structured causal models. So whenever you say that, what's the distribution of Y given an intervention in X, then that needs to be mathematically formalized in order to then make statements about when you can actually learn that causal effect from observational data. This will be the big task of causal inference. And it's quite intuitive, to me at least, that the way we do this is that we say, if we intervene in variable XA, then that means that we stop the mechanism of XA to work. Like we now assign XA a value and not leave it to the parents and the noise term of XA to determine its value. So we intervene in the system and set it to some value. We can do that, right, in an experiment. And then we look at the change in the distribution of the other variables. For example, XC here, given an intervention in XA set to X prime, will in general not be the same as the conditional distribution of XC, given XA has the value X prime. So here it's just we see it, and here it's we intervene. This distribution here is generated from this observational structure causal model here, while the value, the distribution, the interventional one we are actually interested in is generated from this intervened structural causal model, where in the graph you would delete the arrows going into the variable. So it's a thought experiment to define all the quantities mathematically rigorously and then be able to reason about them. So there's two types of tasks you can broadly say in causal inference, and they are based on different sets of assumptions. So one is to utilize qualitative causal knowledge in the form of directed acyclic graphs that can include observed but also unobserved variables. Like here, you may have you may know the qualitative relations between X, Y, Z, and L, and you may also know that L is actually unobserved. But then you can still draw a graph between these, or you may represent the unobserved variable by this bidirected arrow. So those are two different graphs to represent these, and they can be digested by causal methods. And one example was this aerosol cloud example, but you might have much more complex graphs. And it is then in this framework, your task as a researcher to draw this graph qualitatively. And then that will allow you to quantify causal effects given, for example, X on Y, the distribution of Y given X, given do X. Another basic task is that of learning causal graphs based on general assumptions. So here you make less assumptions, but you still have to make some assumptions I will talk about later. But you want to learn which are the causal edges here. What are the arrows actually among these nodes? And I will now explain these two more. So in causal effect estimation, the precise description of the task is you're given a causal graph and data from the observational distribution, so just the observed data, and your goal is to compute the causal effect of a hypothetical intervention. So you want to know this quantity, which, as we saw before, would actually require to meddle with the system, and you want to learn that as a function of the observational distribution. And that is what causal inference achieves to do. So, for example, here, if we now have the system and generate some toy data here, and we actually intervene in the system and set X to some value, then we get this black line on average as an expectation as a response. So that's our causal effect. It's just the regression parameter in this intervention data. On the other hand, if you do a regression on the observational data, then first thing you notice is that the data is a different data set. It's these other dots here, which come from just looking at X and Y as it is coming from the observational data from the distribution. And if you perform a regression in this observational data of Y on X, you will get something else than the causal effect. The reason is that there is this confounding here by L through Z. And now the causal regression here, you could say, would be to fit Y as a function of X, that's the target, the cause. I mean, Y is the target and X is the cause variable. And causal inference here, we would tell you here, well, to deconfound this relationship, you have to add a Z in the model. That would be another factor in this linear regression model, if we are here only aiming for linear relationships. And if you do so, then actually the line that you get is here the red line, but it's completely overlapping with the black line. And there's a small error bar here. So you see that then you estimate the same quantity that you would get if you were able to intervene in the system. That's always the target here. And what we did thereby is a regression coefficient y beta here of y on x given also z is nothing else than the expectation of y given do x set to 1 minus the expectation of y given do x set to 0. So that's some function of the interventional distribution. So what causal inference did here is go from a quantity that has this do, which you can in principle not intervene in the system, you cannot estimate it yourself, and relate that to a quantity in the observational distribution, which is just this regression coefficient. So causal inference gives you kind of the recipe, or we call the estimate how to do that. Maybe I skip that. It's just for more complex graphs. There may be more than one way to achieve this causal estimate, and some are better in terms of their error, and that is what was the topic of this paper last year. So that basically solves the problem of, okay, which of these many different regression models that you could perform in principle that all give you the causal effect is best in terms of statistics. And it's, for example, here, Z2 and Z3 rather than Z1. And now the little excursion to the time series case. What if we now have a time series representation? So we have the same causal graph here, x2, x1, x3, but unfolded in time. So you would then, for example, represent x1, x2, x3 at different time points, and then could be interested in the effect of x1, not just at one time point, but at multiple time points. Maybe you are interested in what is the response to an impulse, for example, where x1, as shown here, is set to some pattern over time, like a time pattern. For example, there's an El Nino event which has this shape, and you want to know what's the causal effect of, well, this kind of impulse on the variable x3 here, and that might look like this, for example, just for illustration. So the only difference here is that this graph is now unfolded in time, but it's still a graph, and it's a cyclic graph, and that whole framework is modified just slightly to account for time series. So that was the first framework where you would assume that you know qualitatively what the causal graph is. And now the more challenging task that you only know the nodes of your graph and want to make some general assumptions and then estimate the causal graph from the observational distribution. So an illustration of this are these assumptions are in the constraint-based causal discovery framework by this Pittsburgh group are the Markov assumption and faithfulness. And what they essentially say is that they relate a dependence between the random variables to a causal relation between the nodes in the graph. So the first one, the Markov assumption, says that if you measure a statistical dependence, then that must come from some indirect or confounded causation. It doesn't need to be a direct causation. It just means that there must be some mechanism that creates this dependence. It's not by chance. And the faithfulness assumption goes the other implication. If you measure that two variables are independent, not dependent, then that means that there is no causal relation between the two. And another assumption that some methods use, not all I will show, is that of causal sufficiency. You assume that these four variables are enough to describe your whole system. It's self-contained in that sense. There's no other variable that causes two nodes in the graph. And the way these assumptions are used to learn causal relations is as follows. So these methods, they would, as a general idea, start with a fully connected graph where these links are still not oriented. You don't know in which direction they go. And then they use conditional independence constraints. So we go to the data and we measure the dependencies between the variables. And maybe in this case, if you measure that V and W are independent, and V and W are both conditionally independent of Y given X, then we use these assumptions now. So the faithfulness assumption says that if there's this conditional independence, then there's no causal relation. And here we try to learn the causal relation. So that means we remove these, we use this faithfulness as an assumption to remove these links that are among pairs of variables that are conditionally independent. So that's the first step. And then we can reason further, namely, could it be that the causal relations among these three variables down there are of this form, that X causes V and W? Well, if we look back at the observed finding, V and W are independent, but in this graph, if this was the true mechanism of the underlying data, then X should make V and W dependent. But since they are not dependent, we can rule this out. And in the same way, we can rule this out, because also that would lead to a dependence between V and W, and the same for this one, under these assumptions. So we use, again, the faithfulness assumption to say that they are independent, so there cannot be a causal relation. That means that V and W must both cause X. Otherwise, you cannot explain this relationship. So we concluded for the underlying graph that, and that's a collider motive, that is the basic workhorse of causal constraint-based discovery algorithms. And now we can even orient the upper link, because if that was the causal graph, then, for example, V and Y would be independent, but we have observed that they're dependent and become independent given the node in the middle, X. So the only way that, the only graph that is in accordance with these assumptions and these observed relationships is this causal graph. And we have not used any time order here. So this is really what this whole, they didn't think much about time actually in their methods. You wouldn't find the word time series in these works in the previous the beginning years. Now we have made a strong assumption here, namely causal sufficiency. So what really surprised me when I first read about it is that you can even go without it. You can even make statements about causal relations without making this assumption. So what if there could be, in principle, latent variables? We can first reason about some latent variable that confounds X and Y, if that in principle can be. And we still use Markov assumption and faithfulness, and we still assume these conditional independence relations to be true. And if we now reason about this graph, then again, this is not consistent with the underlying data, because if this was the graph, then there would be no relationship between V and Y. So in this graph, L makes Y and X dependent, but L cannot make Y and V dependent. And you cannot have a dependence through a collider. So this means that if this was the true graph, then V and Y should be independent, but they are not independent. So the only way this can work is that X causes Y, potentially indirectly through some latent variable. On the other hand, for these links here, if this, we can reason about whether this can be a graph structure that explains the above conditional independencies. Maybe someone wants to think about it. Like, would this graph structure be consistent? Like, if this was the true generating process, would then V and W be independent, these two below here? Some nodding here. Yes. Why? Because L makes X and V dependent, but again, you cannot make something dependent through a collider, which is both causal graphs, so that cannot be. And that means we cannot rule this out. And the same for the other side. So the conclusion from an algorithm here would be that graph, which tells you that X is a cause of Y, maybe indirect through some latent variables. And X is not a cause of V or W. You can rule that out, but you cannot rule out that there's a confounder between V and X, or whether V causes X. These two cases are still open. we say that they are part of the same Markov equivalence class because they cannot be disambiguated from these assumptions. So that is really the basis of these methods. And if we actually apply this very algorithm to the toy data example from the beginning, we would get this graph, like without the sufficiency assumption. If we made this assumption that then the little circle marks would go away. So from this graph, we would know that y actually causes x4 and that we should not include that in a model. And we would know that x3 is confounded and so on. So that gives us a much better knowledge of the process and allows us to better construct a machine learning model. And I will not go over other frameworks, but they are all based on different assumptions. So the second line here is about the restricted structural causal modeling framework, and that makes not assumptions using the conditional independence constraints, but it makes assumptions about the functional dependence in the underlying structural causal model and the noise distributions. So I illustrate here one very prominent method that makes the assumption that the noise is non-Gaussian and the relationships are linear. And then you can disambiguate, for example, between x and y their causal direction, if you just have two variables. So whenever you know that the functional relations are linear, and at least one of the variables is doesn't have a Gaussian noise term, you can use this linear model that it's called to find out what the causal direction is. While in the constraint-based framework, if you just have two variables and they are dependent, then you cannot tell the direction apart. Now again to the time series case. The time series case makes some things simpler because you can utilize the assumption that there's time order. So a previous time step cannot be caused by a later time step. It can only cause it, but that's a basic assumption. And you can also make use of an assumption of stationarity, which you have to also assess whether that is true for the sample that you use. So my work has been a lot on this. I kind of extended these constraint-based methods to the time series case and made them more statistically robust. And one method, PCMCI, does not allow for instantaneous causation. That is what PCMCI plus does. So that's basically PCMCI plus would be the analog to the method shown before. And then if you also deal with hidden confounders, then LPCMCI would be the method that would give you these graphs with also bidirected edges, for example. I didn't mention that before, but these methods, they can also result in these bidirected edges, which tells you that there is a latent variable causing both, but there's no direct causation among them. And the other point I wanted to make is that here we have, like at this, what we call summary graph level, we have this feedback between x1 and x2. But fortunately, one of these causal inferences is at like 1 here, and only the other one is contemporaneous. And that then allows to have an acyclic graph, which you can well learn from the data. So it all depends a little bit on the time resolution you have. If it's 2 cores and both links are at the same time frame, then you do have a cyclic relationship, and that's not really. These methods are not made for this. So what they will result in is like with 2 unoriented edges, and then maybe you can reason about whether this is a cycle or not. But they don't tell you that there is a cycle. Yeah. And I talked about conditional independence relations, and in this framework here, you can use a lot of different ones, and they come with their own sets of assumptions. For example, partial correlation assumes Gaussian noise and linear relations. Then I kind of list the ones here that I have in my package. We have versions that deal well with non-Gaussian noise, but still linear dependencies. We have ones that deal well with nonlinear relationships based on Gaussian processes. We have a method that deals with categorical data and mixed variables, where you have one variable is continuous, the other one is categorical, which in natural sciences is maybe not often the case. And yeah, some based on conditional mutual information, which makes even less assumptions about the functional relations, like no assumptions about the functional relations. All right. And finally, a recent addition to this tool is how to deal with multiple data sets. So what if you have like different sites, measurement sites, for example, the FluxNet sites I analyzed in this way. And that gives you more ways to deal with confounding. That's more actually current work in my group. I'm just showing this here, but you can also just utilize the data and have more sample size. That's simple. And also utilizes to overcome non-stationarity, for example. So what if you have strong non-stationarity, but you have 100 data sets, then you can use just a few points from each data set for which you can assume that it's stationary and use the samples from the other locations. That's the idea. And more about causal discovery in general is in this perspective paper. But just a point on how that goes well together with machine learning is, again, like causal inference is rather a framework that tells you how to construct, how to set up your analysis, how to construct your model in terms of what are the inputs mainly. And it can then be very well combined with, for example, machine learning. So for example, if this is the graph and you don't want to make any linear assumptions, previously I showed you the same graph and we had a linear regression of y on x and z, but what if the system is nonlinear? What causal inference tells you is, well, you need to solve this problem. From a causal inference perspective, the problem is solved at this point because on the left-hand side is a do quantity, which is the target. On the right-hand side, it's some integral, but over just the observation distribution. So that you can measure. So you can, in principle, just measure the distributions here, P of y given xz and P of z. If you want to go this route, like just directly estimate it from the data, perform this integral, and then you actually get that y. It's just Bayesian formalism then. But you can also, for example, here use a neural net. For example, here, this inner quantity P of y given xz, you might estimate with some neural net, which models a very nonlinear relationship of y on x and z. And then given that estimator, you just have to perform this expectation over P of z. And that gives you the expectation of y in a nonlinear way. This is just to illustrate that you still use all the power of machine learning, but you combine it with the reasoning from causal inference. Yeah, I mentioned that. Some more challenges in real life, and many of them not yet addressed, unfortunately, but we are working on it in the, I hope with this article to spur also more interest in the method community to develop tools for the real world problems of earth sciences. And another recent topic is that of causal representation learning. That's kind of one of the first variables that tries to address the problem. Okay, what if you don't even know the nodes of your data? Like you just have this mass of data, this gridded data, and you want to even not assume which the nodes are. It's kind of a little bit ill-defined then. So to solve this problem, other assumptions need to be made. But the goal of this field that is more starting than being mature, I would say, is to try to solve like the problem at once of learning the nodes from the graph and their causal relations, or directly learning the functional relations. And now I come to some applications to try to make these concepts more practical also. And before I want to kind of again step back and frame how to actually do an analysis. So how to perform a causal analysis. And that would start with the first question being, and I framed this as questions, assumptions, data, but outside of this, actually, the first question is, what are actually the variables nodes? I mentioned causal representation learning, but what if we are not yet there yet? And you have to define the variables of interest. So you have to define your nodes of interest. That could be some spatial average. It could be some time average, some average of multiple variables. It could be not an average, directly measured, and so on. And that would also come with different variable types. Maybe they're continuous or discrete or event-based. So those are the nodes of interest. And then we come with two rows here, the questions and the causal assumptions, and they are kind of paired together. So I'm now kind of mimicking this hierarchy of Perl in the first table and making it a bit more explicit here. So what if your question is non-causal? You just want to you really only want to learn associations. The good thing is you don't make any causal assumptions. You just need to make some statistical assumptions, but a question of association can be solved with whatever association measures you have, or prediction in the same distribution, like not a causal question like I want to be able to predict under interventions or in a new distribution, but I just want to predict in the same distribution. I know nothing will change. Then that's not a causal question. Then you don't need all this formula. But then we may come to the next kind of step, which may be a question of I just know my nodes and I want to learn the causal links between them. So the question is then to do causal discovery, to learn the causal links among the nodes, maybe their time lags. And that does not come for free. That needs assumptions. So for example, we have to assume the graph type. Is it a type with maybe cycles? I mentioned there's some work in this direction with allowing for latent confounding. And you may make assumptions about having different data sets and their relations, their confounding, and the Markov and faithfulness assumption. That's what I mean by more here. So to learn these graphs, you need to make these assumptions. And they are causal assumptions because they relate the underlying assumed process to data properties, like Markov property, connecting, there's a connection in the underlying graph to there's a dependence in the observational distribution. Another question where you make more assumptions is that of causal effects. That was the order is not changed. The first question, because here I sorted kind of from making less assumptions to making more assumptions. So when you make not assumptions about the general graph type, but you completely specify the graph, you say my assumption about the relations is this qualitatively, and then you are interested to quantify the causal relations, like of X on Y. And I showed you how to do that, for example, in linear regression, and here I show some nonlinear estimate. And then the last layer that I just mentioned on the first slide is that of counterfactuals. There, your assumption is not just the graph qualitatively, it is actually the full structural causal model. Like you need the full thing. That's why you do that in climate science with climate models. And with this model, you can construct then counterfactuals and changing distributions. Now, in addition to these causal assumptions, you will always need statistical assumptions. So be that just about the type of pairwise dependencies, be it the type of multivariate dependencies like linear, nonlinear, and so on. Further, maybe about observational noise, and maybe stationarity of the whole process. I somewhat group that as statistical assumptions. And then you have not assumptions, but you just have that. You have different data sets. They may come in this like multiple data sets, or there may be even interventional data. Maybe you have on a small scale some interventions in a FluxNet site or so, and properties, annoying properties like missing samples. And the things, if you state your problem precisely in this framework, then it becomes digestible for methods. Like it will be for each of these combination of these aspects, there will be a different method that is suitable. And I'm trying to here build a little taxonomy in this paper that is still submitted of how to choose your method based on specifying all of these aspects. And I will walk you through one example now that I'm not completely confident at, but let's see what you think. But maybe there's also time for questions now.
Are there any questions? Yeah.
Yeah.
Yeah, I have a simple one. Can you go back all the way to the slide where it's like the X, L, Y, and Z? That's like the very beginning, right? Yeah. And so if L is latent and it's causing X and Z, can we say without all the generality that X and Z are just associated or not? And the results will be the same.
So here it doesn't matter that L is unobserved, because this formalism here only requires the non-causal paths to be blocked. That's the precise statement. Like, and L is a confounder of X and Y, like this way, But this inference is blocked if you just condition on this variable z here. If you put that in your model, then that effect is removed. So
you had a shorthand, I think. It wasn't like this kind of slide. It was like, and then you like went
this
like,
slide?
the 2-hour model, the 2-hour thing.
okay, yeah, right.
You could just say x and 0 associated.
I think this
Yeah, that one, yeah.
Yeah, so these graphs, this is called an cyclic directed mixed graph because there are two types of edges, and they mean that the error terms are correlated. That's what you were saying.
So they're associated.
They are associated. But I mean,
level one hierarchy.
Yeah.
Okay, thanks.
I mean, what do you mean by? I mean, that's
There's
your.
like 3 hierarchies. Like
You put
one
that in-
is association, one is intervention, and one is counterfactuals, right? And association is like the lowest kind of.
Well, I think the hierarchy concerns the questions you're asking. Well, this is the assumptions you're making. I'm making the assumption that those are my causal relations. There's some variable or more that makes x and z error terms dependent, where this error term is independent of the error terms.
Okay, so
So
then,
this hierarchy is about the questions you have, not about the assumptions you're making.
okay, so x and 0 confounded, and you want to add L there or something.
Yeah. For example, if there's a confounder between x and y that is unobserved, then the theory will tell you, well, there's no way to do it. Because you cannot block that non-causal path.
But you can block between x and z.
Yes, because z is observed.
You can introduce L to block between x and z.
Well, we didn't introduce it. It's just measured. You're lucky that it's measured.
What does that mean? I'm a little confused.
No, you observed. You have data for x, y, and z. That is your observed data. And then you make the assumption that this is the qualitative causal relations among these variables, qualitatively, and you want to measure quantitatively the effect of x on y.
Okay, but what does the role of L play in that? Right? Because we only have x, y, and z in this picture.
It's just a latent variable that you allow to be there.
Okay, we will carry this on after the talk. Are there other questions? Yeah.
Thank you. I just have a quick question. So for the last slide you just showed, it seems after you carry out the causal discovery algorithm, you still have another algorithm called causal effects. So would you like to?
No, this is. It's not that you first. I mean, you could, of course, first do causal discovery and then do causal effects, but this can start at any part of this, any column.
Could you please explain more of the difference between?
Yeah. It starts with what is your question? What is your question? Do you want to just know about associations? Then you can do that. If you want to know what the graph looks like, that is the causal discovery question. That means you have the nodes and you want to learn the causal relations, and that means you need to make some assumptions like faithfulness and Markov and sufficiency. And then you can pick a method that gives you the graph, and then maybe you're finished. Or your question is causal effect. I want to get a number. I want to get the distribution, or I want to learn the interventional distribution or the expectation. And to perform this task, you either first do causal discovery, then you get a graph. Unfortunately, often a Markov equivalence class of graphs, not just one. And then you can use that as a graph and the assumption of this method to perform this quantitative causal effect estimation. Yeah. And then if your question is counterfactuals, you don't only need a graph, you need a full model and distribution of your noise terms even.
So when we have a prediction, could we also have an estimation for the uncertainty about?
Yeah. That's kind of part of the statistics toolbox of any method. So, for example, I mean, I had this example before. Like here, if you estimate the expectation with this neural net, okay, a neural net is not quite made for getting nice uncertainty bounds, but some can, some Bayesian methods, or you just don't go for the fully neural net. But if you make a linear regression, then you will get an error bound of your beta coefficient. And that is then your uncertainty quantification for your causal coefficient. For causal effects, for causal discovery, the outcome is one graph, and Bayesian methods that I listed as others there, they would give you a posterior about among the graphs. So for example, they would do that. Or in this framework, you can do bootstrap to get kind of a distribution of graphs, and then that also gives you an estimate of what the uncertainties are. Yeah, but that's an important point.
Thanks a lot for the great talk. I have a question regarding the difference between PCMCI and PCMCI plus. You just mentioned the PCMCI plus can capture the instantaneous causality. I wonder, can you explain more about what that means by instantaneous? But it can consider the causal and effect within each time step.
Yes, exactly. Yeah.
But I see in this plot, it seems that the x1 and x2, the direction at the same time step, it seems there is no bi-directed arrow between x1 and x2. At the same moment, I mean, for example, at the same moment of t, there is only an arrow from x1 to x2.
Yeah.
There is no arrow from x2 t to x1 t.
No, that's at time t-1. So here, this is the underlying system. But if you visualize that kind of a simplification in the summary graph, you would draw this feedback. Or when you think about, well, I know quantitatively that there's a feedback between, but one is slower and the other one is faster. And then you can represent that in this time resolved graph. And I mean, this whole slide is about learning causal graphs. So for example, PCMCI plus would spit out this graph, while PCMCI would not tell you the direction, it would just give you an unoriented link here. It would give these two circle marks.
So can the PCMCI plus algorithm learn it by itself to learn which direction is faster?
Yes.
Thanks a lot.
By the same reasoning as I showed here. By saying that, like, this cannot be, oh, it must be this one. It's the same logic. Which relations are consistent with the observed conditional independencies? Yeah.
Second question. So when we learn a graph for data that we observe. So how do we know that's going to generalize to different words that we haven't?
You know that when you trust the assumptions you make. Because causal discovery methods in the good methods, they have theoretical guarantees. That means that if your assumptions are correct, and well, if they're not correct, then we cannot help. Then for the infinite sample case, they will give you the correct causal graph. So if your assumptions are right and you don't have errors in your data and you have enough sample size, the graph will be the correct graph, and then that thing should generalize.
Yeah, but then the issue is that, let's say, one of the assumptions that I don't have an unobserved confounder, that might break down. Let's say in the case of climate change, right?
Then either you drop that assumption and use a method that can deal without that assumption. So you would, for example, learn a graph with bidirected edges. And that helps you to understand that, oh, there must be some latent confounder. And that can help you in reasoning about how the system behaves under new environments. But if this is your graph, then these causal links are, or the assumptions were right by which you estimated this graph, then that tells you that under any environment, if you know X and Z, you can have a best prediction model of Y. But it is, of course, if your assumptions are violated, then that kind of introduces an epistemic uncertainty. There's like some unclearness, and you might want to make, we'll actually get to that point. Like you make different assumptions, maybe like weaken your assumptions and see what then results. Then you use a different method or you change your method for that reason, and you get a different result. And that gives you a little bit of a quantification of how do different assumptions lead to different results.
Okay, so we're at the hour. I don't know if you had more.
I
had more slides.
application slides and the conclusion.
Okay, all right. So why don't you go ahead? Of course, if somebody has to leave,
Yeah.
I understand. But I think please carry on.
Yeah, I wanted to do this question before. Maybe. So this is an example. I mentioned that that's not my specialty, but what I looked at here is, and maybe that was a bit of a challenging toy model, the Walker circulation. So we know that there's this feedback, and I thought that I can learn this as a circular relationship by using the following variables. I used the 700 millibar vertical velocity in the West Pacific and Central Pacific regions, plotted here, which are a little bit taken from this correlation map with the Nino 3.4 index. So that's the strongest uplift and downlift regions. And then in between here, I take the zonal wind at the surface. So I kind of take one node a little bit in the middle here, and down here at the surface. And I use era 5 data because that has this variable. And yeah, 1950 to 21. And now I want to kind of iterate or go through this quad, this questions, assumptions, data. So now my first question is that of causal discovery. I've defined these 3 nodes here. I want to learn their causal relations. And before I even choose a method, I have to reason about what other processes are relevant here that I need to take care of. And I call that pre-processing here. So one is that there are some long-term effects. There's a long-term trend in the data. And I show this here as the red line. So I left the seasonal cycle in just for illustration. So there's a strong seasonal cycle in the data. And then there's also overlaid a slowly moving trend. So here I use some estimate of the seasonal cycle and of the long-term trend, some Gaussian kernel thing to estimate this, because these act as confounders that are, if I just ignore it, that are unobserved confounders, and that would lead to a lot of correlations. So I compute these and I remove these from the data. So I, in the end, will subtract the red lines from the black lines. And the other thing that I do is I know that there's even a regime dependence based on El Nino, like the circulation holds for neutral conditions. Under El Nino conditions, the updrifts, the downdrifts turn into updrifts and they change the location. And the pattern is, on the other hand, just strengthened during La Nina years. So I consider only those samples for which I have neutral or La Nina conditions, because there's this underlying regime change, and I want to only analyze data from a regime for which the causal graph is the same. So I put already quite some expert knowledge in here, but that's often what we end up doing. And as another kind of step of checking for statistical relations, I look at the joint and marginal distributions of the 3 variables. So this plot shows you the joint and marginal distributions. They're kind of the same here. And the red lines are the original data. And what I do as a pre-processing step, because they are not quite normally distributed, but in the end, I want to use partial correlation, which assumes normally distributed data. I convert it to a normally distributed data. This is in statistics called like a copula transform, a Gaussian copula. So you transform the marginals, and that will have an effect on the joint distributions and make them hopefully nicer to treat. And finally, here I show lag functions. So I just compute correlation lag functions among all pairs, among different time lags. On the diagonal, you see autocorrelation. So from that, you learn, oh, there's strong autocorrelation. So, and then the causal relations. So the red line is actually the true data. The black line I will explain later. The relations decay at some lag. And from that, I can learn that if there are no correlations at a certain lag, I can restrict my analysis to this time lag. So those are the kind of first steps I do before I dump this into an algorithm. And now I make the following assumptions. I say that, all right, for the sake of simplicity, let's start with the assumption that there's no other confounding. We've kind of chose only La Nina neutral years. We have removed the seasonal cycle. Let's just hope for, or let's assume and see what comes out, that there's no other confounders. Also because if you do not make this assumption, the algorithms get more complex and less reliable. So there's always a trade-off between the more assumptions you make, the more statistically reliable your answer gets. It's the trade-off between variance and bias. So stronger assumptions, more bias, but less variance. I want to be able to deal with lag and contemporaneous links, and I assume linear dependencies also by looking at the scatter plots here, at the distributions. And I choose a tau max of 2 time steps. And I forgot to say that I use bi-monthly data. I average the 2 bi-monthly data to also remove kind of the noise of the weather scale. And to fulfill this data, my data is now a trivariate, just 3 bi-monthly time series data set. It's continuously valid variables. And with that, as a recipe, I will here choose PCMCI plus, which makes these assumptions. And the robust Parkour test allows for non-Gaussianity and still assumes linear relations. So I turned these question assumptions into data and picked a method that conforms with these. And then that's the result I get. So we here find that I don't show the time series graph. There's like I showed a summary graph here, but there's a contemporaneous causation of the Central Pacific on the West Pacific with the blue color here means it's we use a partial correlation test, so it's negatively correlated. And then there's a positive relation at 0 time lag and partially also at lag 1, which is bi-monthly on the West Pacific. And that then feeds back after 2 time steps, like 3 to 5 months on the Central Pacific. And when I look at the literature and look at the kind of the vertical velocities and how long it takes for this cycle to be closed, then this is roughly on par with these types of time lags here. But yeah, I might need to revise this method, this whole example, because this is a complex and very contentious and hotly researched topic. But that's what I did now. Another thing is, what if we do a little bit of a validation? We constructed this causal graph here. What if I construct a linear model that has the same causal links? I estimate the coefficients from the data. I estimate the residuals and their noise covariance. So I basically construct a linear model that has the same coefficients as here, and then compute what lag functions would I get. And then what I get are these black and their confidence intervals. And this is a little bit of a validation of whether this as a mechanism explains, at least partially in this case, the original correlations. So the red lines are the original correlations. Here it doesn't work out well. Here it works out much better. Here it works out somewhat well. So to one degree, I have to, for example, here it doesn't work out at all, but I have to take care of it. This is mass data, and I only look at the winter month. I think I forgot to say that here. And so I don't even assume that it's valid for time lags more than out of the winter season. All right. Now I have a second question. So I will now use this graph as my assumption in a causal effect estimation and mediation task. So I now make the assumptions of the graph. I use that as an assumption now. I did not have any confounding in the graph. I still assume linear dependencies. The data is still the same. And then to perform this, I can use this optimal adjustment, which is this XYZ that I showed. And I can use another method that I did not explain here in this talk, but it's an even simpler method. And with that, I can then unfold this same graph in time. So that's really the same graph, just unfolded in time, and ask like, what is the causal effect of this CPAC on this VPAC, WPAC, West Pacific? In the graph, this is an indirect effect. It goes through the zonal wind and then affects the West Pacific. And so I can estimate this effect by conditioning on confounding. Confounders here are actually just due to the past. So this orange node here is my adjustment. So what I do in the end is I perform a regression of the West Pacific on the Central Pacific at the same time lag, conditioning on the West Central Pacific at lag -1. And if that graph is true, that will give me a correct estimate of the do operation of intervening here on this node, if the graph is correct, of course. Then in the very same graph, I can estimate the effect of the West Pacific, like which is this direct link, which is much weaker here. And what I do here is I analyze the effect of the West Pacific at time lag -1, it's West Central on the West Pacific. And here the relation is, there's a direct link and there's also an indirect link, which is the assumption here. Maybe it's wrong, but what I get is I can here decompose this. I can say how much of this effect is due to the direct link and how much is mediated here through the autocorrelation. That enables to decompose and answer questions of that is called mediation. How much is mediated? All right. I'm not sure I should rather stop here, but I would really love to talk to some of you who are interested afterwards, because I think we still have some time, in a biogeoscience example. And with that, I close. Here, I would actually talk about non-linear, non-parametric causal effect estimation and hidden confounding. All right. That's another aspect. So take-home message. I hope I convey to you an idea of causal inference as a framework to answer causal questions from empirical data, meaning questions about if you would be able to intervene about the system from just the observational data. I discussed two settings. One is causal effect estimation, which assumes a graph with all your domain knowledge. And the other one is causal structure learning, which is learning graphs from the data. I post this kind of recipe or analysis template of state your question in this language, state your assumptions and data that allows you to choose a suitable method. And importantly, it makes your assumptions transparent. Because you could then have one part of your paper saying, okay, if I assume this graph, then I get this effect. And if I assume this graph, maybe there's a slight change. And I've now seen quite some papers, I don't know, in ecology, I reviewed a paper that really very nicely had like this assumption, this assumption, this assumption. And then you can very transparently say, okay, we can argue about the assumptions, but this assumption will lead to this number, kind of this effect. And that is a good way, I think, to use this framework. And I also try to make the point that it goes well together with machine learning or AI more generally, which is able to deal with nonlinearity in complex data sets and so on. And more pointers to software are here. I coded up a Python package. There's PCArc for R, Tetrad for Java. Causal Fusion is a framework for causal effect estimation, which is online, which has more powerful tools available. And CausMe is a benchmark that I try to build more on. Okay, thanks for your patience.
Okay, we'll just take one or two questions if there are any at this point. Yeah.
Sorry, I still have the constant question. So won't the causal discovery process already tell you some information about the magnitude of the causal effects? Why would we want to? It
depends on the method. Like a Bayesian method gives you a score for this graph. It's not really telling you about the quantification of a link. the constraint-based methods, they are based on partial correlation. So you can construct a measure of causal strength. But the thing is, like not this one, but in the previous, this is, I mean, partial correlation is a normalized measure. It's between -1 and 1. And the goal of causal effect estimation is to get at physical causal effects, or in terms of standardized units, while partial correlation is better comparable among completely different types of variables. But so it's a question. So it's also, yeah, you have to choose your causal strength measure. Like the output of PCMCI is, for example, is just the minimal partial correlation of all conditioning sets. It's not that well interpreted, I would say. It's not an interpretation like what happens if I intervene in X, what expectation change I get in Y in terms of the standard deviation if I have standardized data, which is nicer to talk about than causal strength. That's a very vague term.
Thank you, very clear answer. Thank you.
One more question.
So I was wondering if you assume a causal graph, how you can check that the causal graph is correct before doing inference.
Yeah. So on the one hand, you can use causal discovery to learn a causal graph and check whether that is somewhat similar to what you assumed. But causal discovery makes maybe less assumptions and will be subject to the noise of your data and short sample sizes. Or you can test whether the conditional independence relations in your graph are consistent with the data. So if your graph says that these variables, two variables should be conditionally independent, then you can test that whether that is actually true in the data, make some tests, or you compute the log likelihood of the graph using some Bayesian model. So you can do that in several ways. Yeah.
And another question is, in the example you showed, there's always 3 or 4 variables. I was wondering if you have, for example, a climate model with 50 variables.
Yeah.
If you can do inference with many more variables, and then how you can choose what variable you include in your graph. Because I assume like if you ask a question, then you're going to want the variables that you need to answer this question, but it's sort of a bias, right? Because then you choose the variables that you're really interested. So there's
Yeah, you want to include all the variables, like you have maybe some X and target Y, and then you should include the variables that you assume would be confounded of these. And so it's a lot dependent on your choice and how to choose that more data driven. So there's a work that I'm showing you for that reason is where we wanted to explain causal relations among sea level pressure in the reanalysis data set, or actually here in CMIP. And we had gridded data there, of course. And what we did was we tried to reconstruct kind of the autonomous processes that govern these relations. And we were not that creative here. We used rotated PCA because that is often used to reconstruct independent processes, like processes like ENSO or the NAO would come out of such an analysis, for example, if you just dump in the sea level pressure data. And then we use these as the nodes of our graph. And we chose not all of the many components, but we truncated them such that the whole system explains like 90% of the variance or so, like PCA. I mean, we chose as many PCA components such, but that's just, it will very much depend on every analysis.
Okay, well, thank you very much. Let's thank the speaker.